You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Pitfalls in artificial intelligence refer to the recurring mistakes and oversights that undermine system performance, fairness, and reliability. These mistakes are often not the result of malicious intent, but of flawed assumptions, incomplete planning, or neglect of critical details in the development process. Pitfalls can arise at every stage of the AI pipeline, from data collection and pre-processing to model training, validation, and deployment. For instance, a model trained on narrow or biased data may seem accurate in testing but fail disastrously when applied in broader contexts. Other pitfalls stem from overconfidence in metrics, ignoring transparency, or underestimating ethical risks. The presence of these errors reminds us that AI development is as much about discipline and oversight as it is about technical innovation. For learners, pitfalls represent the difference between building models that succeed in controlled environments and systems that genuinely serve human needs responsibly in the real world. Data quality issues are among the most pervasive pitfalls in AI. The old saying, "garbage in, garbage out," applies directly here. Poor input data inevitably leads to poor outputs, no matter how advanced the algorithm. Data can be incomplete, with critical attributes missing, inconsistent, with varying formats and definitions, or inaccurate with errors introduced through human entry or faulty sensors. For example, a medical dataset missing key diagnostic information will train a model incapable of making accurate predictions. Inconsistent data formats, such as mismatched date conventions or measurement units, confuse algorithms and distort results. Inaccuracies, whether from typos, faulty instruments, or transcription mistakes, poison the dataset further. Addressing quality issues requires rigorous cleaning, validation, and standardization. For learners, data quality underscores that reliable AI begins long before algorithms are applied. The robustness of a system is inseparable from the integrity of the information upon which it is built. Sampling bias occurs when datasets fail to represent the population for which the AI system is intended. A classic example is facial recognition models trained primarily on lighter-skinned individuals, which then perform poorly on people with darker skin tones. Similarly, an economic model trained only on urban data may falter when applied to rural populations with different patterns of behavior. Sampling bias is often unintentional, arising from limited data availability or overlooked assumptions about coverage. Yet its consequences are serious, producing models that reinforce inequality or exclude entire groups. Correcting sampling bias requires deliberate efforts to diversify datasets, ensuring that examples reflect the full spectrum of populations and scenarios. For learners, this pitfall highlights the ethical and technical responsibility of inclusivity in AI development. A model that works well for some but fails for others cannot be considered trustworthy or fair, no matter how accurate its aggregate performance metrics appear. Labeling errors are another frequent source of failure in AI systems. Supervised learning depends on accurate labels that connect inputs to correct outputs. When those labels are misclassified or inconsistently applied, the model learns flawed associations. For example, in medical imaging, if some cancerous scans are mislabeled as benign, the resulting system may overlook life-threatening conditions. In sentiment analysis, if annotators disagree or apply inconsistent criteria, models may learn contradictory rules for what constitutes positive or negative tone. Labeling errors may arise from human fatigue, lack of expertise, or inadequate guidelines for annotation. They distort the learning process by embedding incorrect signals into the training set. For learners, labeling errors illustrate that AI is not immune to human mistakes; it often amplifies them. Careful annotation practices, quality assurance checks, and expert oversight are essential to minimize this pitfall and build models that reflect reality rather than error. Historical bias in data embeds past inequalities into AI systems, perpetuating them into the future. Datasets often reflect the social, economic, and political contexts in which they were created. Hiring records may reflect decades of gender or racial discrimination in employment. Criminal justice data may encode systemic disparities in arrests and convictions. If these datasets are used uncritically to train models, the biases become automated, giving the illusion of objectivity while reinforcing unfair outcomes. For example, predictive policing systems built on biased arrest data may disproportionately target marginalized communities, deepening cycles of inequality. Addressing historical bias requires recognizing that data is not neutral but shaped by human choices and societal structures. For learners, this pitfall emphasizes that AI is not free of history, it is deeply entangled with it. Responsible development means questioning the origins of data and actively correcting for the injustices it may conceal. Confirmation bias in design arises when developers build systems that unconsciously reinforce their existing beliefs or expectations. This bias is not about the dataset but about the mindset of those creating the model. For instance, a team designing a financial model may assume that certain demographic groups are higher risk and build features that reflect this belief, unintentionally confirming their assumptions. Similarly, researchers eager to demonstrate progress may highlight results that support their hypothesis while overlooking contradictory evidence. Confirmation bias narrows perspective, leading to systems optimized for one worldview rather than reality. Mitigating it requires deliberate diversity in development teams, critical peer review, and openness to contradictory findings. For learners, confirmation bias illustrates that AI is shaped not only by technical inputs but also by human psychology. Vigilance against personal assumptions is just as important as careful data preparation in building trustworthy systems. Proxy variables are features that appear neutral on the surface but act as stand-ins for sensitive attributes such as race, gender, or socioeconomic status. For example, a postal code may seem like a benign input in a credit scoring model, but if neighborhoods are segregated by income or ethnicity, the model effectively uses postal code as a proxy for sensitive characteristics. This can result in discriminatory outcomes even when direct references to protected categories are excluded. Proxy variables are tricky because they often hide in plain sight, seeming innocuous while carrying deep correlations with sensitive traits. Detecting and addressing them requires careful analysis of feature impacts and fairness audits. For learners, proxy variables highlight the subtlety of bias in AI. Discrimination can occur not from explicit prejudice, but from hidden correlations that embed inequity into models without obvious warning signs. Measurement bias occurs when the metrics or tools used to evaluate models misrepresent their true performance. For example, a model might achieve high accuracy by focusing on majority classes in an imbalanced dataset, while ignoring critical minority cases. Metrics such as accuracy may suggest success, even when models systematically fail vulnerable groups. Similarly, flawed sensors or inconsistent survey instruments can introduce bias at the measurement stage, feeding skewed signals into training. Measurement bias distorts evaluation, creating a false sense of confidence in systems that do not serve their intended purpose fairly. Addressing it requires careful selection of metrics, such as precision, recall, or fairness measures that reflect real-world goals. For learners, measurement bias emphasizes that numbers are not neutral. Evaluation choices shape how performance is perceived, and poorly chosen measures can mask serious flaws in AI systems. Overfitting remains a classic pitfall in AI development, particularly when models are trained too aggressively on limited data. An overfitted model memorizes the quirks of the training set rather than learning generalizable patterns. For example, a facial recognition system may perform flawlessly on the dataset it was trained with, but fail miserably when encountering new faces. Overfitting is especially dangerous because it often appears as excellent performance during training, hiding its fragility until deployment. It arises from excessive model complexity, insufficient data diversity, or inadequate regularization. Preventing overfitting requires strategies such as dropout, cross-validation, and data augmentation. For learners, overfitting demonstrates that more is not always better larger. More complex models are not inherently stronger if they fail to generalize. The goal of AI is not to excel on familiar cases, but to adapt robustly to the unfamiliar. Underfitting represents the opposite problem: models that are too simple to capture meaningful patterns in the data. An underfitted model performs poorly both on training data and on unseen cases, showing that it has failed to learn the task at all. For instance, attempting to fit a straight line to data that clearly follows a curve leaves large errors unaddressed. Underfitting may result from overly simplistic model design, insufficient training time, or ignoring key features. The pitfall lies in assuming that simpler is always better, neglecting the complexity needed to reflect reality. For learners, underfitting emphasizes the importance of aligning model capacity with task complexity. The art of AI lies in balance. Too little complexity produces shallow, ineffective learning, while too much produces brittle memorization. Both extremes undermine reliability, reminding us that model design requires nuance and calibration. Automation bias refers to the human tendency to over-rely on AI systems, assuming they are more accurate or reliable than they actually are. Users may defer to algorithmic recommendations even when they conflict with common sense or expert judgment. For example, a doctor may trust an AI diagnostic tool's prediction despite signs that it is wrong, simply because it carries the authority of technology. Automation bias can lead to poor outcomes by reducing human oversight and accountability. It is particularly concerning in high-stakes fields like aviation, healthcare, or law enforcement. Mitigating it requires training users to critically engage with AI outputs, designing systems that explain their reasoning, and maintaining human authority in decision-making. For learners, automation bias shows that pitfalls are not only technical, they are also behavioral, shaped by the ways humans interact with and trust AI systems. Feedback loops are another subtle but damaging pitfall, where AI systems reinforce the very patterns they are trained on. For example, predictive policing tools that send officers to neighborhoods with high reported crime rates generate more arrests in those areas, feeding back into the data that those neighborhoods are high crime. This creates a self-perpetuating cycle of bias, independent of actual conditions. Similarly, recommendation systems that promote popular content increase its visibility, making it even more popular while sidelining diverse options. Feedback loops highlight the dynamic nature of AI. Models do not just reflect the world, they shape it, altering the data that will train the next generation of models. For learners, this pitfall underscores the need for continuous monitoring and intervention, recognizing that AI systems can influence society as much as society influences them. Lack of transparency is a recurring issue in AI, especially with complex black box models like deep neural networks. When stakeholders cannot see how a model arrives at its decisions, accountability diminishes and trust erodes. For instance, a denied loan application without explanation leaves applicants unable to understand or contest the outcome. Transparency is not about revealing every technical detail, but about providing enough interpretability for users and regulators to assess fairness and validity. Documentation practices, explainable AI methods, and communication strategies all play roles in addressing this pitfall. For learners, lack of transparency demonstrates that accuracy alone is insufficient. Trustworthy AI requires clarity, accountability, and openness, enabling humans to scrutinize and understand the systems that increasingly shape critical aspects of their lives. Ethical blind spots occur when developers ignore broader responsibilities such as fairness, privacy, or consent during deployment. A system may function technically but still cause harm if it disregards ethical concerns. For example, deploying facial recognition in public spaces without consent raises serious questions about surveillance and individual rights. Similarly, using personal health data without adequate safeguards breaches privacy even if the model achieves high accuracy. ethical blind spots emerge when technical achievement overshadows human impact. Addressing them requires embedding ethics into every stage of development, from data collection to deployment. For learners, this pitfall emphasizes that AI is not only about solving technical challenges, but also about honoring societal values. Ethical vigilance is as crucial as algorithmic precision in building systems that deserve public trust. The consequences of bias and pitfalls in AI range from technical failure to profound societal harm. Discriminatory outcomes can marginalize groups, undermine fairness, and deepen inequality. Organizations face reputational risks when flawed AI systems are exposed, as well as legal risks in regulated industries. Trust in technology erodes when systems are perceived as unfair, opaque, or harmful, slowing adoption and innovation. At an individual level, biases in credit scoring, hiring, or policing can affect livelihoods, opportunities, and safety. These consequences highlight why vigilance in detecting and correcting pitfalls is essential. For learners, the lesson is clear. AI is powerful but fragile. Its benefits depend on disciplined practices that anticipate and address pitfalls proactively, ensuring systems are not only effective but also ethical and equitable in their impact. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Detecting bias in AI systems is the first step toward addressing it, and this requires both statistical analysis and diagnostic tools. Developers often begin by disaggregating performance metrics across subgroups to see whether certain populations experience higher error rates than others. For example, a voice recognition model may work well for speakers of one accent but fail for others. Statistical fairness tests can reveal disparities in accuracy, recall, or false positive rates across demographics. Diagnostic tools such as fairness dashboards help visualize these patterns, while more advanced approaches use counterfactual testing to see whether outcomes change when sensitive attributes like race or gender are altered. Detecting bias is not about assigning blame, but about surfacing hidden imbalances that might otherwise go unnoticed. For learners, bias detection illustrates that AI is not a neutral mirror of data. It reflects and amplifies what it is given. Identifying those reflections is essential to building systems that can be corrected and improved. Fairness metrics provide structured ways of quantifying whether AI systems treat groups equitably. Demographic parity measures whether positive outcomes are distributed evenly across groups, while equalized odds assess whether error rates are similar for different demographics. Other metrics, such as predictive parity, ensure that probabilities of success are consistent across subpopulations. Each metric captures a different perspective on fairness, and they often conflict, requiring careful judgment about which aligns best with the domain. For example, in hiring, equal opportunity may be emphasized to ensure qualified candidates from all groups are equally likely to be selected. In healthcare, minimizing disparities and false negatives may take priority to ensure no group is denied critical diagnoses. For learners, fairness metrics show that equity is not a single number but a complex set of trade-offs. Evaluating fairness requires not only mathematical rigor but also ethical clarity about the values being upheld. Mitigating bias can occur before training even begins, through pre-processing techniques that balance datasets and correct inputs. One approach is resampling, where underrepresented groups are oversampled or overrepresented groups are undersampled to create more balanced datasets. Data augmentation can also expand minority classes with synthetic examples, enriching diversity. Another method involves reweighting, assigning different importance to examples so the model learns from them more equitably. For instance, a dataset of loan applications might be adjusted so that decisions do not skew unfairly toward one demographic. Pre-processing ensures that biases embedded in historical data are not simply inherited by the model. For learners, pre-processing demonstrates that fairness is not just about algorithms but about shaping the very foundation of training. Correcting imbalance at the start gives models a better chance of producing fair and inclusive outcomes later. Bias mitigation can also occur during training, where algorithmic adjustments enforce fairness constraints. Some methods penalize the model when outcomes diverge across groups, nudging it to balance performance more evenly. Others adjust loss functions so that errors affecting underrepresented groups carry greater weight, pushing the model to correct them. For example, a hiring algorithm might be trained with fairness-aware objectives that reduce the chance of replicating historical discrimination. These approaches embed fairness directly into the optimization process, making it part of how the system learns. However, they also raise challenges, as enforcing one definition of fairness may reduce performance in other areas. For learners, training stage mitigation shows that fairness is not an afterthought but a principle that can be woven into the very mechanics of learning. It illustrates how technical design choices can carry ethical weight, shaping the outcomes models produce. Post-training mitigation strategies provide another layer of protection, addressing bias by monitoring outputs and applying corrective measures. Calibration can adjust decision thresholds for different groups, ensuring that outcomes are more equitable. For example, a credit scoring system might alter cutoff points to balance approval rates without retraining the entire model. Auditing systems can continuously evaluate outputs for disparities, triggering alerts or interventions when unfairness emerges. External fairness filters may also be applied, re-ranking or adjusting outputs to minimize bias. These measures recognize that bias may persist even after training and must be managed dynamically. For learners, post-training mitigation emphasizes that fairness is not a one-time fix. It requires continuous vigilance, with systems designed to adapt and correct themselves as they operate in real-world conditions. Human oversight remains critical in detecting and addressing bias. While algorithms can highlight disparities, only human judgment can interpret their significance in context. Domain experts provide knowledge of what fairness means in a given field, whether healthcare, education, or finance. Ethicists and social scientists add perspectives that go beyond technical metrics, considering cultural, legal, and societal implications. Human reviewers can catch subtleties that algorithms miss, such as whether a system unintentionally stigmatizes or marginalizes certain groups. For learners, human oversight demonstrates that fairness cannot be automated entirely. Technology must be complemented by human responsibility, ensuring that decisions about equity and justice are guided by broader values than mathematical formulas alone. AI is powerful, but it cannot define fairness on its own. Humans must remain accountable for the outcomes it produces. Transparency practices are essential for preventing blind reliance on AI systems and for enabling accountability. Documentation tools such as model cards describe the purpose, training data, performance, and limitations of models, providing users and regulators with clear insights into how systems operate. Datasheets for datasets offer similar transparency about how information was collected, what populations it represents, and what biases may exist. These practices help organizations and stakeholders make informed decisions about deploying AI, reducing the risk of misuse. Transparency also builds trust, as users can see not just outputs but the processes that produce them. For learners, transparency highlights that AI is not only about performance but also about communication. Systems must be interpretable, documented, and open to scrutiny if they are to be considered reliable partners in decision-making. Without transparency, even accurate models can erode trust by appearing as mysterious black boxes. Accountability structures ensure that responsibility for AI outcomes does not vanish in the complexity of development and deployment. Governance frameworks define who is responsible for monitoring models, responding to problems, and ensuring compliance with ethical and legal standards. This might include bias audit requirements, independent review boards, or clear chains of accountability within organizations. Accountability prevents the diffusion of responsibility, where failures are blamed on the system rather than on those who designed, trained, or deployed it. For example, if an autonomous vehicle makes a harmful decision, accountability structures determine whether responsibility lies with engineers, operators, or companies. For learners, accountability underscores that AI is not self-governing. People remain responsible for the consequences, and robust governance is essential to ensure that responsibility is neither ignored nor deferred. Cross-disciplinary review brings together perspectives from ethicists, social scientists, and affected stakeholders alongside engineers and developers. This collaboration broadens the definition of fairness, ensuring that systems reflect societal values rather than narrow technical criteria. For example, in designing a predictive healthcare model, input from doctors, patients, and ethicists ensures that outcomes align with both clinical needs and human dignity. Cross-disciplinary teams can spot blind spots that technical experts might miss, such as cultural implications or unintended harms. For learners, cross-disciplinary review illustrates that AI is not just a technical project but a social one. Building inclusive systems requires contributions from many voices, ensuring that fairness and accountability are not defined solely by those with technical power. This diversity of perspective makes AI more robust, equitable, and trustworthy. Bias in natural language models has become a highly visible issue, as these systems often absorb harmful stereotypes from large text corpora. When trained on internet-scale datasets, language models learn not only useful grammar and knowledge, but also prejudiced associations. For example, they may generate biased statements, linking professions to certain genders, or reinforcing racial stereotypes. This bias can surface in outputs, leading to offensive or discriminatory content. Addressing it requires filtering training data, applying fairness constraints, and monitoring outputs carefully. For learners, bias in language models highlights the scale of the problem. When datasets are massive, harmful patterns can spread invisibly and pervasively. It shows that scale does not eliminate bias. It magnifies it, demanding careful, ongoing oversight of how models generate and use language. Facial recognition systems have been criticized for unequal accuracy across demographic groups, performing significantly better for lighter-skinned men than for darker-skinned women. These disparities arise from imbalanced training datasets and flawed evaluation practices. The consequences are serious, as facial recognition is used in sensitive areas such as law enforcement, border control, and surveillance. Misidentification can lead to wrongful arrests or discriminatory monitoring, undermining trust in both technology and institutions. Addressing bias in facial recognition requires improving dataset diversity, adopting fairness-aware algorithms, and applying stricter evaluation standards. For learners, this pitfall illustrates the real-world stakes of bias. It is not an abstract concern, but a tangible risk to individual rights and social justice, reminding us why vigilance in evaluation and fairness is essential. Predictive policing systems demonstrate another dimension of bias, as they often reinforce systemic inequalities. These systems use historical crime data to forecast where future crimes are likely to occur, but because historical data reflects biased policing practices, predictions often perpetuate over-policing in marginalized communities. Officers sent to these areas generate more arrests, which are then fed back into the system, reinforcing the cycle. This feedback loop creates the illusion of objectivity while deepening inequality. For learners, predictive policing illustrates how bias is not just a flaw in data, but a dynamic process where AI reshapes reality in unfair ways. It warns that deploying AI in sensitive contexts requires extraordinary care, as even well-intentioned systems can entrench injustice when built on biased foundations. Regulatory approaches are beginning to address bias directly, requiring audits, fairness standards, and accountability frameworks. Laws such as the European Union's AI Act propose rigorous testing and transparency requirements for high-risk AI applications. In the United States, discussions around algorithmic accountability are shaping policies that mandate bias audits for systems used in hiring, credit, and housing. These frameworks aim to ensure that fairness is not optional but required by law, with penalties for violations. For learners, regulatory approaches show that AI development does not occur in a vacuum. It is subject to governance shaped by democratic and legal institutions. Compliance with these frameworks is not just about avoiding penalties, but about aligning technology with shared values of justice and equality. Cultural and contextual awareness is vital for fairness, as definitions of equity and acceptable trade-offs differ across societies. A fairness measure appropriate in one country may not align with values in another, depending on cultural norms, histories, and legal systems. For example, approaches to privacy differ significantly between Europe and the United States, shaping expectations for how AI systems handle data. Awareness of these differences ensures that AI systems deployed globally respect local values rather than imposing a one-size-fits-all model of fairness. For learners, cultural context illustrates that fairness is not purely technical, but deeply social. Building equitable AI requires humility and dialogue with the communities affected, ensuring that technology respects diversity rather than flattening it. Building an ethical AI culture within organizations is perhaps the most powerful mitigation strategy. Culture shapes daily decisions, guiding whether teams prioritize fairness, transparency, and accountability. An ethical culture includes regular audits, cross-disciplinary input, and clear escalation pathways for concerns. It rewards developers for identifying risks, not just for achieving performance benchmarks. Without such a culture, even strong policies may fail in practice, as incentives push teams to prioritize speed or profit over responsibility. For learners, ethical culture highlights that trustworthy AI is not just the result of technical fixes, but of organizational values. Embedding fairness into the DNA of an organization ensures that it persists not as an afterthought but as a central principle, guiding innovation in a direction that builds trust rather than undermines it. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.